All right, good afternoon, class. I'm going to have to break these down into parts just because of how much information there is to understand and go through before we even start talking about phases within microstructures. So part one is microstructures practical interpretation, and what we'll be learning or going over in this particular segment is the terminology that's used to describe microstructures, and that terminology will cover the grain size and shapes, phases, or the orientation of phases, cast versus wrought products, cold form versus hot formed products, inclusion materials, imperfections within the microstructure, and then some of the surface features that you may come across. So the whole purpose is to not only understand but also use the common language that would basically give you the ability to describe a structure to somebody, and then they can in turn draw it out. Okay, so you have to be able to visualize what the reader or what the person is describing and picture it. So one of the first things to start covering is the simple thing: grain size and shape. What are we talking about when we're looking at microstructures is how the grains are shaped. So are they equiaxed like the image on the left? And what I'll do is I'll zoom in a little bit here. So this is an equiaxed grain structure, and it's equiaxed in the sense that if you were to look at any of these grains, and I have my pencil hopefully ready. How come my pencil's not? So if I were to look at any of these grains, that's so weird, it uses a hand to draw. You should be able to see that it's equiaxed, where if I were to take this distance and this distance, they would predominantly be about the same, okay? Now this is a ferrite grain structure, and as we mentioned before, with nitol, you don't get the full grain size, because if you were to look at this area here, this looks like a very large grain, and you see very faint grain boundaries. Okay, so but for the essence of this, an equiax grain structure would be, they're about the same in the two different orientations. Now when we look at an elongated grain structure, as what we see over here on the right, this grain structure looks pancaked. Okay, this is the deformed version of what we saw in the equiax grain structure. So the nice thing about this is it will identify the rolling direction. So let me just, how come it's not letting me use my pencil? Anyway, the rolling direction in this case would be in this orientation, okay, whether it's this way or this way. That's because when you're looking at the grains and how they're deformed, you see that the grain structure, the grains are elongated in this orientation and they're shorter in this orientation, okay? So that gives you that pancaked grain structure. So this material on the right would actually have a slightly higher hardness than the material with an equiax grain structure on the left. So now when we're looking at talking about grain size and shape, we're looking at what is considered to be a uniform grain structure, or something that might be mixed or duplex grain structure. When you have a uniform grain structure, it is essentially one grain size throughout the entirety of your sample. Mixed or duplex grain structures are typically made up when you have a large grain, as you can see in this image here. You see this large grain, okay, and that is mixed in with a bunch of smaller grains. So this would be a duplex or mixed grain structure. If you're able to take measurements of the large grain, then you would have two different grain sizes you can measure, and that would be the one of the smaller grains and one of the larger grains. Looking at phases, so a uniform distribution of phases would be what you see here in the left image. You see an even amount of ferrite, and which is your white phase, and you see an even amount. So there's my ferrite, and this is my perlite. The distribution of those phases are pretty uniform throughout the entire image. Whereas when you look at the image on the right side, you can see a linearity going in this direction here. Okay, so you see areas that are carbon rich or rich perlite, which I will use orange to distinguish perlite. So here's your perlite phase. And then you have low carbon or poor carbon rich regions, and I'll make that one purple, and those are your regions like this right here, okay, which is essentially all ferrite. So you get that banded grain structure. This is more of the type of grain structure you would identify with a hot forming process, and I'll discuss that a little bit more in detail as we move to the next images. Another type of phase that you can, or phase distribution that you can run into, is something that you see on the screen. It's a cluster. So it's very random. These are typical of cast products or chemical segregation within the sample. So since we're talking steel in this case here, you have your areas that are rich in perlite, which are your darker phases, and then you have your regions that are rich in ferrite. Okay, and that's a chemical segregation. Could be a solidification artifact on how these materials then solidified. So looking at castings, the image on the left is a macro etch of a cast iron ingot, and the microstructure is given on the right. Now this is at 50x magnification, but you see this, it's considered to be a dendritic structure. That's the way it's solidified. So the macro that you see over here on the left, each of these regions, okay, all the differences in contrast is how the light is reflecting off of those grains. Okay, so these are actual grains. That means this guy right here is the size of that grain. But what does it look like in the middle? That's where you take an image like this. This is your micro graph of what you're seeing under the microscope, and it's a dendritic structure based on you can get differences in your dendritic structure based on how quickly or slowly you cool the sample. Faster cooling will result in the dendritic structure to be more close together, so the interdendritic spacing is smaller, whereas if you allowed more time or a slow cool, then the interdendritic spacing will be much larger. Okay, so what this really is here, since this is a cast iron, I have a lot of carbon content. These white phases that you see in here are cementite. So that's your Fe3C. Okay, and then your darker phases are your perlite. So I'll just put a P over the perlite. Now, how does that differ from a wrought product? Well, here's a macro of a forge, not a casting, but of a forge, and you can still see the flow lines. Now, these aren't grains, These are the flow lines caused by the, for one, the etch, but how the material was flowed and formed into that shape. And when you look at it under the microscope, this happens to be a 4140 material. The differences in contrast that you see here on the left are reflected in the microstructure when you're looking at it. The darker regions versus the lighter regions is an chemical segregation. So one of the things that you note are these little inclusions right here, which are these dull gray inclusions in your material. This is a steel. Those are likely manganese sulfide inclusions. They tend to be sitting in an area where the etch revealed a light, or the response to the etch was light, versus the areas above it, which are darker. So that's where you get chemical segregation within the material. So cast irons, we have two different types. You have nodular cast iron, and you have cast iron that has flakes. All it is a difference in the morphology on how graphite is dispersed throughout the material. Nodular cast iron tends to have a better ductility versus your flake cast iron. But this is, once again, any type of analysis on graphite, it's best to analyze in the as polished condition, hence the reason why none of these images were etched. Depending on the heat treatment of these, your microstructure around it is going to be very different, and in some cases with the flakes, you can hide some of these smaller little guys, like this guy here, but some of the bigger ones are all going to be obvious. But if it's a pearlitic structure, then chances are you can mask some of your graphite. Then you have inclusions. Inclusions that are impurities versus inclusions that are formed based on additions of elements that are done on purpose. The image on the left would be an example of impurities that you do not want to see in a high strength, low alloy steel. Those are in the form of manganese sulfide. So pipeline industry, any of the high strength, low alloy steels, it's unwanted. All it really does is reduce your fracture toughness of the material. But why would you then add sulfur into steel? Sulfur is typically added in the image on here on the right as for better machinability. You're able to cut the samples better, machine whatever parts you need to, but those would not be something that you would want to depend a lot on for structural applications. So looking at some of the imperfections that you can discover or reveal and observe in metallography is porosity. So you have to be able to distinguish the difference between gas and shrinkage porosity. Cracks, intergranular versus transgranular, folds and or laps. You have intergranular attack versus intergranular oxidation. And then you have some surface imperfections that can be identified as well. So starting with porosity, the image on your left is gas porosity, and the image on your right shows an example of shrinkage. These are both images in an aluminum alloy. So how do I know to distinguish the differences between each? The image on the right, the image on the left actually has the gas porosity, which are more spherical or circular. If you're looking at it on a two-dimensional plane, it would be circular in nature. So when you're looking at this guy here, let me get the blue out. So this one and this one would be all gas porosity. They're pretty circular in nature. think of a bubble being captured three-dimensionally. It would look like a bubble, and so that's what these would look like if you were to encapsulate the rest of it. If you grind further into the material, they could get smaller because you're past the halfway point, or they could enlarge because you have not reached the halfway point. The other two, if I'm looking at the image on the right, speaking of the dendritic structure, as you see the what's revealed over here in the microstructure, the shrinkage porosity is just where the metal was not enough metal to fill all the void during solidification. So it's gonna look finger-like. So if you make a fist and you look at your fingers, that's kind of what the shrinkage porosity looks like in these materials. So this image over here on the left, you could probably say that that one would be shrinkage porosity as well, okay, because it's not spherical in nature. And you look to see, if you made a fist, you can see some of these little finger-like morphology within that porosity. Looking at cracks, so the one on the left is an intergranular crack that was formed in high-strength low-alloy steel. You're saying, well, how is it intergranular? This would have followed prior austenitic grain boundaries. So a special etchant is used to reveal those grain boundaries in heat-treated steels, such as this one here, which has been quench and tempered. The image on the right is an example of stress corrosion cracking with transgranular crack paths. And what these terms mean is intergranular is following the grain boundaries. Transgranular is cutting across the grains. So if I were to zoom in a little bit on the, oops, not draw, but if I were to zoom in a little bit on the one that's transgranular, you can see that the cracks are cutting across the grains. They're not following grain boundaries. Okay, this one over here looks more jagged. So the prior austenitic grain boundaries might be a little bit on the small side. But if you picture, if this was a grain, something along those lines, and then of course the grain on the top, this is typical in quench and tempered materials that crack due to embrittlement conditions. Folds and laps is another defect that we can find through cross sections. In the as polished condition, you can see a line that has been formed, and all it really is a material that has been folded over on itself. Thread laps are very common, and so if you're rolling threads during the forming process, there's a chance, if you have a burr in the material or just material that wasn't fully cut, what ends up happening is or a misalignment even with the machine, the material will fold over upon itself, and in doing so, the material will actually, after you etch it, will show deformation. Okay, so this microstructure, you could tell it's deformed, but the deformation around the crack tip is even more so. So the deformation that you would see in this region here would lend this to be a thread lap or a fold of material. Attack versus oxidation. So intergranular attack is typically something that is embrittling to the material. When you're looking at this image, zoom in a little bit, the intergranular aspect of it, this is in the unetched, so as polished condition. You can see the cracks. You can actually see where some of these grains have actually pulled out. So there used to be a grain right there, and there used to be a grain right here. And you can see that by how the mold material, which I'm going to highlight in green. This is your mount material up here. So your mounting material has formed along this really well. You can see that either the material is shifting, but this is a large gap between the material and the mounting material itself. But nonetheless, when you're looking at the interfaces here, these are not filled with oxides. These are all cracks. And some type of attack is happening here. Something embrittling is going after this material. When you're looking at intergranular oxidation, the oxidation aspect, these are oxide filled. So this was a grain boundary. So picture it nice and sharp, but because of oxidation, you're losing material. So the cracks or the intergranular features are not going to be as sharp as they were in the intergranular attack example. These are more blunted, they're oxide filled, and you got to think about it. This is three-dimensional, so you're wondering, well, this is an example of something. Well, it's not open to the surface, so how is this part of intergranular oxidation? Well, this is a three-dimensional material that we're only getting a two-dimensional representation of. So once again, if you grind further, you can grind away the these areas, or you can grind in and reveal more. It depends on how severe the attack was on the microstructure. Some surface features that you can come across for metallography. The image on the left, especially for steels, is decarburization. And you can see how the etch response, it looks white at the tips of the threads, but when you're comparing that to the microstructure, the base metal microstructure down here, it's darker, but up here it's lighter. So carbon has essentially diffused out of the material, and hence the light etch that is the light etch response. The more carbon, the darker. So if it was carburized, you would have a much darker outer surface compared to your base material. Alloy depletion is also another example of a surface flaw that occurs, especially in high temperature exposures. Instead of it just being carbon that is being removed from the material through diffusion, you're now looking at aspects of, like, say, chromium, aluminum, titanium, something that can react with the surface environment. And if it forms oxides on the surface, then it's depleting your base metal microstructure of its alloying element, and it's going into something else. Surface contamination. This would be the contaminated layer. This also, once again, high temperature exposure. When you're allowing the material to react with the atmosphere, especially at high temperatures, you get stuff that dissolve into, such as oxygen can react with the material of the base material. Then you get, when you start having that happen, if you notice the, zoom in on this, but if you notice just under that layer, what you end up seeing is a light etch response just underneath over the whole sample. And that's because alloys have been depleted from this region to react with whatever was out here in the atmosphere to form this stuff on the surface. And it's really hard to identify in metallography what exactly that surface is composed of. So chemically, it has changed. And since there's a change in chemistry, you have a change in properties. So the real way to go back and to identify what this layer is, is to perform EDS mapping, and you can identify what if you have an increase in oxygen content, nitrogen content, anything along those lines at that interface. So I'm hoping that with some of these slides, it helps identify just a general overview of metallography and what to expect. I'll be putting together part 2, which will now jump into the phases of ferrous alloys and break down the differences between your plain carbon, high strength, low alloy, tool, and stainless steels. So look for part 2 coming up. I will be attaching this document, terms and definitions, and that will be on Blackboard for you to download and start reviewing, because now we're getting into that aspect of class where the terminology will become important. Thank you for your time, and we'll see you for part 2.